All right. Wow, imagine having to go after Will. What a great talk. As you just heard, my name is Braydon Coyer. I am a husband and a father to two perfect little girls, and that is like the perfect job for me. I absolutely love it. I'm from the Dallas, Texas area, and this is my first time in Miami, so I'm super stoked to be here with you guys to share the stage with so many awesome other speakers and to just soak up all of this information that we've learned today. This is a picture of my little family. They're back in the Dallas area. Shout out to my wife who's making sure the house doesn't burn down, that the kids are okay and fed. She's doing the hard work so I can be here with you guys talking about Tailwind CSS. And speaking of Tailwind, we all do this, don't we? We've been using Tailwind for years. We open up our IDE, we type in a few classes, it works, and we move on. We're kind of like on autopilot mode. And really quick, I want to introduce you to a few friends of mine. This is Skid, and that's Mitch. And they're going to pop up throughout this talk. Skid is a very curious developer. He likes to dive in deep and understand what's going on. And Mitch, well, he's been using BG Indigo 500 for everything for the past 4 or 5 years. I can't really blame him though. It kind of seems like what everybody's doing, it's fine. But let's assume that Mitch is working on a component and he throws BG Indigo 500 onto a div and boom, we get a nice blue-violet background. He doesn't think about it, he moves on. That's the deal with Tailwind. But I want to challenge you to spend the next 20 minutes or so with me thinking about what actually just happened. Mitch typed a string into a class name prop, and somehow that turned into real CSS that the browser understands. But what actually just happened? Like, what's going on under the hood? Does Tailwind just pre-generate CSS for every potential utility class? Because if so, that seems like really inefficient. Or how does it handle arbitrary values, like when you want to set a custom background color to a value that isn't included in the default palette? Skid started asking these same questions, so he did what any developer would do. He jumped into the source code, and that is what this talk is about. It's a guided tour through the Tailwind processing pipeline from the moment you add a utility class onto an element to the moment that it becomes CSS that your browser can understand. The Tailwind processing pipeline has 5 different stages, and the first one that we'll look at today is called content collection and class discovery. So Mitch typed BG Indigo 500 onto a div, and before Tailwind can do anything with that utility, it first has to find it in Mitch's code. And that's where the scanner comes into play. The scanner's job is to figure out which files in your project are using Tailwind. And the scanner is pretty smart too, because it doesn't waste its time, it doesn't burden itself with files or folders that it knows it doesn't need to look into. Things like your node modules, your lock files, your images, or even your CSS files, which took me a minute to think through, but it makes sense, right? Those things are just ignored. And it's smart enough so that way when you're saving a file, it just needs to reprocess that single file and see what changed, rather than scanning through your entire project again. Now, a quick bit of history. In older versions of Tailwind, you had to manually tell it where your files were and where to look for utility classes. Raise of hand, who remembers the content array in the Tailwind config file? Yeah, that's where we had to manually list out all of the files and the paths where we wanted Tailwind to work. And if you forgot one, it just wouldn't work. I know we've all been there. In version 2, in version 3, in older versions of Tailwind, this was handled with JavaScript, is where it would try and find these files, it would try and find these utility classes, and we all know that JavaScript isn't the fastest thing in the world, so this process could get a bit slow. So because of that, Tailwind version 4 moved this functionality over to Rust, introducing a new internal engine called Oxide. And guys, I know we're at a React conference, we're all JavaScript developers, but from what I hear, Rust is like super quick, like on a whole new level compared to JavaScript, right? And so because of this, Tailwind is able to utilize that speed and just figure out which files are using Tailwind. In fact, Tailwind version 4 drops the JavaScript config file entirely, which is really nice. I think that's a really great change. Okay, back to content collection and class discovery. So after the scanner has identified, yep, here's a file, I think it has a utility class, it hands it off to the extractor, which will read through your JSX, your HTML, your view file, whatever it is, and it will pull out that utility class. But think about this. Tailwind works with React, it works with Angular, and all the other JavaScript frameworks. And for the most part, the way that we add CSS classes to elements doesn't vary a ton between frameworks. React uses the class name prop, and Angular uses class, but for the most part, we're still applying a utility inside of a string, so no big deal. But Angular also has this conditional binding syntax, where the class name sits inside of square brackets with a dot in the middle. And this is a little bit of a different shape. And Svelte, too, has its own way of handling conditional classes, as do many other frameworks. And so the question becomes, how does the extractor handle all of this without needing a separate parser for every framework? The answer is boundary detection. And the extractor doesn't actually parse React truly. It doesn't actually parse Angular truly. It doesn't care what framework you're using or what language you're writing in. It does understand what characters can surround a class name, no matter where it appears. And it does this by grouping characters into 3 distinct groups. First, you have common boundaries. These are things like white spaces or quotes, basically anything that can come on either side of the utility class. And then you've got before boundaries, so characters that come before the utility class name, and in our conditional example, we had class.flex. That period, that dot, would be classified as a before boundary because it comes before the utility name. And of course, after boundaries, characters that come after our utility name, like the closing square bracket in that same example. Okay, so we understand how the extractor knows where classes can start and end on an element. But we haven't talked about how it actually separates them into individual utility candidates, because you can apply more than one CSS class to an element, right? Let's use a slightly more complex example, building on the utility that Mitch added to his markup. When you write something like this, the extractor needs to understand that the entire thing, MD, hover, BG indigo 500/50, is an entire candidate, not just a bunch of individual pieces. And it's not trying to understand what hover means. It's not trying to understand what indigo 500 means. But what it needs to know is where the candidate starts and where it ends in that class name. And the way it does this is through a family of specialized Rust machines inside of the extractor. Now, don't overthink the word machine too much. We're JavaScript developers. I've never written Rust, but it's just a small function that knows how to recognize a specific shape in a string. And the entry point is here, the utility machine. And it will delegate work to submachines based on the first character that it sees. And you can see a few of those machines listed here. We have the arbitrary property machine, the named utility machine, the modifier machine, and the variant machine. And so from our example, the variant machine recognizes the variant segments like MD and hover. The named utility machine would mark BG indigo 500 as the core utility, and then the modifier machine picks up the /50 at the end. And together, they agree that the whole string is a complete utility candidate. So the scanner found BG indigo 500 in Mitch's code. The extractor pulled it out off of the element and put it into this bag of strings, because remember, it's doing this throughout your entire repo. So every new utility class it finds, it's going to add to this bag of strings. But knowing a utility exists isn't the same as understanding what it means. And just a little sidebar, at this point, all of the Rust processes are complete. So the scanning, the extraction, all of those are handled with Rust, and all of our future states and steps will be handled with TypeScript. And TypeScript comes into play here in the second step, the candidate parsing step of the pipeline. So after Oxide passes that bag of string utilities off to TypeScript, the first thing that it does is run each one through a function called parse candidate. And this is where meaning starts to appear for the first time, because up until this point, the whole string has just been a flat string. It has no meaning attached to it. The extractor confirmed that, yes, this is a utility, but Tailwind doesn't know how to map it to anything. So the initial job of the parse candidate function is to split the string so it can separate variants from the base utility. And just like Mitch, you might be saying, I'm a JavaScript developer, I know what to do. We can just do a dot split on the colon and move on with life, we'll be fine. And for simple cases like hover, colon, flex, that would probably work well. But Tailwind allows us to do some crazy things. We can do something like this, where we have 2 colons in this utility, and the troublemaker is the colon inside of that arbitrary value between color and var. So the split can't just happen it can't happen anywhere. It can't happen inside of parentheses or in square brackets. It needs to happen at the top level only. And to help with that, Tailwind has this function called segment. And this function will track the depth of a utility using a stack. So every time it sees an open parenthesis or an open bracket, it will push to the stack. And every time it sees a closed parenthesis or a closed bracket, it'll pop. And it only splits the utility when the stack is empty, meaning that we're at the top level. And so after splitting, it's able to identify the base utility, and then everything that comes before it is defined as a variant. And so after all of this work, what does parse candidate actually give us? It gives us this, which is a candidate object. And a candidate object is just a structured representation of the utility class. It knows that the root is BG, and it knows that the value is Indigo 500. And if we had any modifiers or variants, it would track those here. But even at this point, Tailwind doesn't know how to resolve these values in the object. That comes in the next step. The theme resolution and CSS generation step is my favorite. It's where things start to get really interesting, although maybe a little bit more complex, so try and stick with me here. I think the best way to explain this is to just trace the data all the way through each step and see how it transforms. So we take our candidate object from the previous stage and we send it into a function called compile AST nodes. Every utility in Tailwind has a compile function tied to it. So when compile AST nodes is called, it runs the base utility's compile function, which you can see here. And I want to call out the resolve theme color function. You might be able to see it there. It's because that's what takes something like Indigo 500 and actually turns it into a real CSS value. And under the hood, it's calling theme.resolve, which returns a CSS variable with a fallback value. That CSS variable will be passed back up to compile AST nodes, where it's wrapped into a rule node with the correct selector, which is really interesting because that's the first time we've seen this. So in Mitch's case, the selector would be .bg indigo 500. Now this object that you see here is called an abstract syntax tree, or an AST node. And this still isn't CSS yet, obviously, right? But it's a structured representation of CSS. And at this point, Mitch is a little confused. And maybe you are too, that's okay, because we've been talking about these candidate objects, and now we're talking about abstract syntax trees, and they're kind of the same, but they're kind of different. So what is the deal? The candidate object represents the input. It's just a parsed version of the class string. It knows that the root is BG, it knows that the value is Indigo 500, but it has no idea what CSS it maps to. On the other hand, the abstract syntax tree node represents the output. It knows that the CSS property is background color, and it knows that the value is a resolved CSS variable, and it knows that the selector is .bg indigo 500. So one is about what was written, the candidate object, and the abstract syntax tree describes what will be generated, which is what we're going to look at right now. And this is where the toCSS function makes its debut. It takes an AST node and it generates CSS one line at a time. So take a look at the code block above. We're not going to go into all of the details, but basically at a high level, if the AST node is identified as a declaration, it just returns a single line. But if that AST node is identified as a rule, it injects the selector, it opens up our block with a curly, it walks through the children recursively, so it'll call itself, where we'll hit that first if statement, we'll add individual lines of CSS, it gets to the end, we break out, we close the rule, and what we end up with is something like this, which is hopefully exactly what you would expect it to look like. Now we're almost there. We have valid CSS, but before we ship our product to production, we should talk about optimization. After Tailwind generates all of the CSS, it gets handed off to Lightning CSS, which is just a Rust-based CSS processor, and it's triggered inside of the optimize function, which you can see here. And to be super clear, Lightning CSS is not part of Tailwind itself. It's a separate tool, but it's deeply integrated into the pipeline, and it does a lot of heavy lifting for us. For example, it handles browser compatibility by automatically adding vendor prefixes, which is really nice for me because I always forgot to add auto prefixer in my side projects. It'll also handle minification, so stripping white spaces and really trying to optimize our selectors to make that file size as small as possible. And it supports modern and experimental CSS features like nesting and the new experimental @custom media @rule. So it'll compile those down for older browsers. And all of this happens automatically. You don't have to configure anything, which is really nice. It just happens as part of the build. And here's a fun detail, actually. Tailwind calls Lightning CSS twice. The first pass handles things like nesting that toCSS function might have generated. And then the second pass further optimizes the output by trying to combine selectors where it makes sense or trying to tidy up the final CSS. It's trying to do everything possible to make this as efficient as possible. But there's one question I think some of you might still be asking, and you're probably like, Braydon, goodness gracious, where does Tailwind put all of this CSS? Where does it live? And we'll answer that as part of the final stage of the processing pipeline. And it's dead simple, because guys, you've all seen this. All of the generated CSS gets inlined right where you import Tailwind in your base CSS file, which means that your CSS entry point is the output location for Tailwind. So let's go ahead and zoom out. Our utility class started as a string in Mitch's markup. The scanner found the file. The extractor pulled it off of the element and created a candidate using boundary detection. The parse candidate function started to create some structure and give it meaning for the first time. The compile AST nodes function resolved the theme values and built an AST node. Our toCSS function turned that abstract syntax tree into CSS. Lightning CSS came in and optimized that for the browser. And finally, Tailwind placed the final CSS in the root CSS file. And that is how Tailwind works. That's the full pipeline. Now, maybe you came in today, first day of React Miami. Maybe you were like Mitch. You typed some utility classes. You moved on. No problem. No big deal. But now you've seen what actually is happening under the hood. And you're not supposed to think about this every day, right? I mean, that's what makes this such a great tool, is that it gets out of your way when you're using it. But when you do look under the hood, it still holds up, and it's intriguing, and it's insightful. And I hope that's what this was, a behind-the-scenes look at Tailwind CSS and how tiny utilities become optimized production CSS. Thanks, y'all.